Hello student, hi, I'm Vipin Mishra and I welcome you all on the IMS GATE Academy. I hope you all are preparing well for the GATE exam and in the meanwhile you are enjoying our GATE Booster series as well. Yesterday we had a very fascinating session where we have discussed some very important questions and concepts. If you really want to experience the same kind of scenario in all other subjects, subscribe our channel and go to our playlist and see there we have already taken the GATE booster sessions for the subjects like digital, control, measurement, machines, network as well. So yesterday we discussed for this particular subject power electronics that we I'm taking here. So yesterday we have discussed about power semiconductor devices and DC to DC converter. In the continuation, today I will be discussing the rectifier and inverter, two such topic in which most of the students really struggle. So if you are attending this session, this will not be a cause of concern for you, because like the way we have approached for the topic like DC to DC converter and semiconductor, here I am going to give you the same experience as well. So let's get started. So first of all, I will start with the topic rectifier. So tell me first of all, have you people enjoyed the last session? Good evening, Nikhil. Good evening, everyone. So here I am going to start with the rectifier. So when it comes to rectifier, guys, the important topics of rectifiers are single phase rectifier. You can expect a question from single phase full wave rectifier, controlled rectifier and uncontrolled rectifier. Three phase rectifier, three phase full converter will definitely give you a question in the exam. And after that, effect of source inductance, one such topic in which across all the students struggle. Okay, so this will not be the case after joining this session. Now when it comes to the weightage of this particular topic, you can expect a 2 to 3 marks of questions from this particular topic. So let's get started. So here comes the first question. So just read this particular question with me and we will try to solve it together. Okay, so what this particular question says is the source voltage and current in a single phase AC to DC converters are Vt equals to 200 root 2 sin omega t. The voltage is sinusoidal, but the current is also periodic and it has three sinusoids, sin omega t, sin 3 omega t and sin 5 omega t, like that. And you have to calculate the power drawn in kilowatt by converter and current distortion factor as well. So you have to calculate the power drawn in kilowatt by converter and the current distortion factor. Okay, so let us proceed for this problem and see how we can solve this problem very easily. So guys, as you can see, the voltage is sinusoidal. The voltage that we have is sinusoidal, but the current is having multiple sinusoids. So there are two possibilities. If suppose this voltage and current both are sinusoids, if suppose the voltage that we have is Vm sin omega t, pure sinusoid, and if the current is also a sinusoid like this, let's suppose the voltage is like this, Vm sin omega t plus phi, and current is Im sin omega t plus theta. If suppose these are our voltage and current, both are sinusoidal, in that case you may calculate the power. The power will be Vrms into Irms cos phi minus theta. But in case, and that is a general case in power electronics, the voltage and current, although they may be periodic, but they are not perfect sinusoid. This may be the case, and this is the general case of power electronics. In any of the converter, if you see, for example, if I talk about rectifiers, the voltage that you are giving is a sinusoid, but the current that you are giving is periodic, but it may not be sinusoid. It may contain so many harmonics as well. So if this is the case, let's suppose you have, this is the case number 1. So this is a simple case. If we have like this scenario, you can calculate the power directly by using this formula, and you have a better practice of calculating the power in this manner. But if suppose the voltage that you have is like this. V naught, this is the case 2 that I am going to discuss. V naught plus summation n equals to 1 to infinite Vn sin omega t. Let me write it n omega t, n omega t plus phi n, and the current is I naught plus summation n equals to 1 to infinite In sin n omega t plus theta n. So if suppose the voltage and current are given in such a manner, what will be the power in that case? So in order to calculate the power for this particular case, guys, we will use this particular expression. The power will be given by V naught into I naught. We will multiply both the DC terms, and after that we will use this expression half n equals to 1 to infinite Vn In cos phi n minus theta n. So now you can expand this particular formula and you may have an expression like this: V naught I naught plus half V1 I1 cos of phi 1 minus theta 1 plus V2 I2 cos of phi 2 minus theta 2, and so on. So if the voltage and current are given in such a scenario where they are having more than one sinusoid present, which is a general case in power electronics, in that case you may calculate the power in this particular manner by using this particular formula. Okay. Now in our case, coming back to the problem, the voltage which is given to us is Vt equals to what? The voltage given is 200 root 2 sine omega t. Okay. And the current is having first, third and fifth harmonic. So what will happen, guys, if suppose the voltage given to us is 200 root 2 sine omega t, and the current that we have is, the current given to us is 10 root 2 sine omega t minus 45. Then we have 5 root 2 sine 3 omega t minus 30 we have, and after that we have 2 root 2 sine 5 omega t plus 60. So this is the voltage and current given to us. Okay. Now voltage, as you can see, is a pure sinusoidal waveform, sinusoidal signal, isn't it? But the current is having multiple sinusoids. So this may be the case when you have given a perfect sinusoidal voltage to a non-linear load, then that particular load will produce this type of current. Okay. So if you see from this particular expression, if you compare here, what will be the power, guys? What will be the power here? Can you tell me what will be the power here? If we calculate the power from this expression, what is going to be the power? Can you tell me what is going to be the power from here? One more thing I would like to tell you, if current is having multiple harmonics, you can calculate the RMS value of current by this particular formula. Under root n equals to 1 to infinite I of n RMS square. So you can calculate the RMS value of current, the individual RMS, sum of individual RMS values. Okay. So how can you calculate the current, guys? If you see, the first expression that we have is 10 root 2, 5 root 2 and 2 root 2. So we can calculate the RMS value by 10 root 2 divided by root 2. This will be the RMS value of first component. Then 5 root 2 divided by root 2. This will be the RMS value of second component. And then we have 2 root 2 by root 2, the RMS value of the third component. Okay. So on solving this, you will get 129 or by solving this you can get 11.35 ampere as the RMS value. So this will be the RMS value of the current. Okay, this will be the RMS value of the current. Now what to do? Here we have the voltage given to us, and the voltage is 200. Voltage is 200 root 2 sine omega t. The voltage is 200 root 2 sine omega t. So the RMS value of voltage will be what? This will be 2 root 2 divided by root 2, or we will get 200 volt. So what will be the power here? Power we can calculate by VRMS, IRMS and cos of phi 1. Okay. So VRMS is 200 and IRMS is 11.35 and cos of phi 1. Phi 1 we can calculate by looking into the phase displacement between the fundamental components. So here we have sine omega t and here we have omega t minus 5. So phi 1 will be 45 guys, cos of 45. So when you will calculate this, you will get power as 1.60 kilowatts. So do we have any answer which has this option? Yes, of course we have. Option B has the answer. Okay, so this will be the power. Now again we have to calculate the current distortion factor as well. So you know that the current distortion factor CDF, the CDF is given by fundamental component RMS value divided by the total current RMS value. So the fundamental component is having the maximum value as 10 root 2. So its RMS value will be 10 root 2 divided by root 2, and the total current is having an RMS value. We have calculated this 11.35. So finally when you solve this, you will get the current distortion factor equals 0.88. So this is how we can calculate. Good evening Saurabh. So this is how we can calculate the power and the current distortion factor if the voltage and currents are given in this particular manner. Okay, yeah. So you may expect this kind of question in the upcoming GATE exam. So many times this particular question has been asked in the exam, so you can expect this kind of question in the exam as well. Okay, now talking about the next question. In the next question we have a separately excited DC motor when fed from a 230 volt 50 hertz single phase fully controlled bridge converter. Okay, single phase fully controlled bridge converter is involved here. With a firing angle of alpha, the motor is initially running at 990 rpm from a 200 volt DC supply. When fed from converter, the motor runs at 490 rpm. Then we have to find the firing angle. Now we have to calculate the firing angle. So what has been given to us? A separately excited DC motor when fed from 230 volt 50 hertz single phase full bridge converter. It is, the motor is initially running at 990 rpm from a 200 volt supply. So initially the voltage is 200 volt and the speed of motor is 990 rpm guys. Okay. Now in the second case, what is given to us is when fed from the converter, the motor runs at 490 rpm. Okay. So when we have fed it from the converter, then let's suppose the voltage is V2 and at that time the speed is 490 rpm, I think. Yes. Then the speed is 490 rpm. So we have to calculate what will be the firing angle of the converter. We have to calculate the firing angle of the converter. Very good, Nikhil. We have to calculate the firing angle of the converter. So guys, if we do V2 upon V1 divided by N2 upon N1, we can calculate the voltage V2, which will be N2 upon N1 into V1. Now N2 is 490 upon 990 into what is V1 here? It is 200. So you will get V2 as 98.98 volts. So this will be the voltage V2. Now since this is a this motor is being operated with the help of a single phase full bridge converter, So you know that in case of a single phase full bridge converter, the output voltage average value is 2 Vm by pi cos alpha. Now this output voltage is 98.8. 2 into what is Vm here? Vm is 230 is the source voltage. So Vm will be root 2 into 230 divided by pi, that is 3.14 cos of alpha. So from this particular equation, if you solve this particular equation for alpha, the alpha comes out to be 61.45 degrees. So do we have any option which contains this particular option? Yes, we have 61.45. So this is how we can solve this particular question as well. This is a very good question, okay? Initially the motor is operating at some voltage and some it is having some speed. Now it is operating at some other speed when fed from the converter. Now we have to calculate the firing angle. So this is how we can solve this particular problem, guys. Okay, yeah. Now moving towards the next problem, see this particular problem. A single phase full wave controlled converter is fed from a source of 100 pi sine 100 pi t, and it is feeding a RE load with R equals to 20 ohm and E equals to 600 volt. Okay, so what has been given to us? Let me just write this. It is feeding an RE load where R is 20 ohm and E is given to us, which is 600 volt. If it is operated at a firing angle of 135, guys, firing angle is 135 degrees, okay, then the power in the circuit with respect to the load will be, what will be the power in the circuit with respect to the load? Whether the load is delivering power or it is absorbing the power, we have to comment on that as well. And the options are 3.24 kilowatt of power, whether absorbed or delivered, and 5.24 of kilowatt power, whether it is absorbed or delivered. We have to comment on that as well. So how do we solve this particular problem, guys? If you see here, the firing angle given to us is 135. Firing angle is 135 and the load is being fed by a full wave controlled rectifier. So you know that when the firing angle alpha is less than 90, then what happens? When the firing angle is less than 90, V naught, which is 2 Vm by pi cos alpha, it is positive, and the load side KVL will be V naught equals to E plus I naught R. But when the firing angle is greater than 90 degree, in that case what will happen? This particular expression of V naught will give you a negative voltage, and in that case you have to invert the battery terminal, because now it is acting as a line commutated inverter, isn't it? So we have to invert the battery terminal. So now E must be reverse, and what will be the KVL of the load side? It will be V naught equals to minus E plus I naught R. So this will be the KVL of the load side. Okay, this fact you have to remember while solving this particular question. Now what we have to calculate here is the power. So first of all, let me put here the values. So what is E here? E is 600 plus what is I naught? Do we have I naught? No, we don't have I naught. I naught is not given to us, and R is 20, isn't it? Yes, R is 20. So this will be the V naught. Now after that, guys, firing angle is given to us. So from the firing angle and from the expression of the output average voltage of single phase full wave converter, we can calculate V naught. So V naught will be what? Vm is 100 pi sine 100 pi t. So Vm will be 100 pi divided by pi cos of alpha, which is 135. So from here you can calculate V naught, which will come out to be minus 1.4 volts. So this is the V naught that we have calculated. Okay. Now again come in this particular equation. Again, if you come in this particular equation and if you put the value of V naught, which is minus 144 1.4, this is equals to minus of 600 plus 20 I naught. So from here you can get the value of I naught. So after solving this, you will get a value of I naught, which is 22.93 ampere. So this will be the I naught value. So we have calculated I naught, which is 22.93 amperes now. Okay. So what will be the output power? Output power will be V naught into I naught. So just put the values. This will be V naught into I naught. What is V naught? 141.4 into what is I naught? I naught is 22.93. So what will be the power, guys? The power will be 3.24 kilowatt. Okay. So do we have any option? Yes. In option A and B, we have the same value, 3.24 kilowatt. But can you comment whether the load is delivering the power or it is absorbing the power? Whether the load is delivering the power or it is absorbing the power. What will be the case here? Since the output voltage is having a negative value and the alpha value is greater than 90 degree, guys, this particular converter will be acting as line commutated inverter. So what will happen in that case? The load must be feeding whatever DC it has to the load, to the source. So load must be delivering the power to the source. Okay. So what will be the answer? 3.24 kilowatt of power delivered. So in this particular case, the load will be delivering the power to the source. So that will be the correct answer. So this is how we will solve this particular case. Okay. This problem is very confusing, guys. Do not remember to do this particular thing. Do not remember to do this particular thing. If you will remember this thing, you can very easily solve this question. If firing angle is less than 90, then the voltage V naught will be positive and your converter will be acting as a rectifier. So the load side KVL will be V naught equals to E plus I naught R. But when the firing angle is greater than 90, V naught will be negative. In that case, what you have to do? In that case, you have to reverse the battery terminal. You have to reverse the polarity of E. Okay, because the converter is now acting as a line commutated inverter. So what will be the load side KVL? The load side KVL will now be minus E plus I naught R. Okay. So if you can remember this small fact, you can solve this problem very easily. And when alpha is greater than 90, of course, the load will be delivering the power to the source. Okay. Now, just see this particular problem right now. In this problem, this is the similar kind of case we have. So what has been given to us is a 3-phase full converter is feeding a battery from a 3-phase supply of 230 volt 50 hertz. The battery EMF is 208 volt. So what is given? Just let me just write these facts. E is what? E is given to us, which is 208 volt and its internal resistance is 0.5. What is the value of R? The R value is 0.5 ohm. Okay. On account of inductance connected with the battery, charging current is kept constant at 18 ampere. The charging current I naught is kept constant at 18 amperes. If the power is flowing from DC source to the AC load, yeah, means the load is delivering power. So power is flowing from where to where? Power is flowing from load to source. Okay, means your load is delivering power to source, and when this is the case, alpha is greater than 90 degree. The firing angle delay for the same current will be. So you have to comment what will be the firing angle delay. So you know that when the load is delivering power to the source, of course, the firing angle has to be greater than 90. So it cannot be below 90. So I think option A and B cannot be the correct answer. Either option C or D must be the correct answer. Now you have to comment which option is correct. Okay, so I am giving 2 minutes to you for this particular problem, and let me check whether you are able to solve this or not. So your time starts right now. You have 2 minutes. Just try to solve this. Okay, let me be aside. Last 5 seconds, guys. Okay, so again we have the same case, but we have 3-phase full converter right now. So guys, what will be the load side KVL? Load side KVL, when power is delivered from the load to source, so the load side KVL will be V naught will be minus of E plus I naught into R. So what is E here? E is 208 plus what is I naught? I naught is 18 and R is 0.5. So 18 into 0.5, and what will be the V naught here? 208 plus this is 9. So we will get minus 199 volt as V naught. Okay, so this will be the V naught here. Now for 3-phase full wave converter, we know that the output voltage average value is what? The output voltage average value is 3 VML upon pi cos alpha. Now average value we have already calculated, which is 199, 3 into VML, the maximum value of the line voltage. So this will be the root 2 into the line voltage given to us, which is 230 here. So we will put 230 here divided by 3.14 cos of what is the firing angle that we have to calculate. Okay, so when you will put the values here and calculate the firing angle, that will come out to be, it will be 1929.8. 129.8. So do we have any option which has the same option? Yes, option D. So option D is having the same option. Okay, so this is how, by remembering the fact that when alpha is greater than 90, what will be the load side KVL, and when the load is delivering power to the source, in that case the load side KVL will be minus E plus I naught R. Okay, we have to reverse the battery terminal, and then we will apply the KVL, and we can calculate the firing angle by applying the converter output voltage as well. Okay, yeah, so this is how we can solve this particular problem. Okay guys, normally what happens in case of rectifiers, the source that we give is a sinusoidal source, and when this sinusoidal source is given to the non-linear load, it produces a current which is periodic but not sinusoidal. So I am taking you towards the first problem once again. So I am taking you towards the first problem once again. So what you have seen here is when both current and voltage are sinusoid, you can simply calculate the current by this expression. But when the voltage and currents are not sinusoid, you can calculate the power by using this expression. Okay. So if you look into this expression, we do not have V naught I naught here, and if we compare, we do not have any, we only have fundamental component, that is V1 of the voltage, and all other component of voltage are absent here. Okay. So guys, this is absolutely correct that we can calculate the IRMS value like this. But when it comes to the power, guys, when it comes to the power, here we have to use I1 RMS. Okay. Here we have to use I1 RMS because all other components of voltage are not present. So when you see this particular expression, we have written this absolutely correct. So when you see this particular expression, here we have V1 I1, V2 I2. But guys, voltage only has the V1 component and current has I1 component. Current has I3 and I5 component as well, but the voltage does not have I3 and I5 component. So all these factors will not be there. So when you will calculate the power, only fundamental component will be there. So instead of putting 11.35 here, the RMS value of fundamental component will be what? The RMS value of fundamental component will be 10 root 2 by root 2, that is 10. Okay. So it will be 2000 by root 2. So how much is 2000 by root 2? Can anybody tell me? How much is 2000 by root 2? Can you just tell me how much is 2000 by root 2? Yes, I am waiting for your replies, guys. I think this will be 1.4 kilowatt. Okay. So this is what you have to do. We have applied the correct formula in order to calculate this expression, but we have to take care of this fact, guys. See, here we have V1 I1, here we have V2 I2. But if you compare this, V as only having the V1 component, I is having I1 component, I3 component and I5 component as well. But we do not have V2, V3, V5, all components to multiplied. To get multiplied with the current. So in order to calculate the power, what you will do, you will only use the fundamental component. Okay. When it comes to calculate the total RMS value, we have did exactly the correct things. You have to sum up all the RMS value of all the sinusoids and you will get the total RMS current. And when it comes to the correct distortion factor, fundamental is divided by total and you will get the current distortion factor. Okay. So you will get the current distortion factor. So this option must be 1.4 kilowatt. Okay. So just make this small correction here. Now moving towards the next problem. Just read this problem with me and tell me how do we approach to solve this problem. In this, we have a single phase full converter that delivers power to a resistive load. Okay. We have a single phase full converter which is delivering power to the resistive load of 10 ohm. Now for an AC source voltage of 230 volt, the RMS output current will be. If the AC source voltage is 230 volt, we have to calculate the RMS value of the output current. Okay. So for that we have to calculate the RMS value of output voltage as well, isn't it? So guys, if you see here, if the applied voltage which is sinusoid, if I draw that voltage and that voltage is this much, this is pi and this is 2 pi. and let me call this to be alpha angle. Similarly here we will have 2 pi plus alpha. Now when you will plot the output voltage, if this is Vs, and now when you will plot the output voltage, guys, so at the angle alpha, during the positive cycle you will trigger T1 and T2. So what will happen, T1 and T2 from alpha, they will follow the input voltage up till the moment pi, and after that what will happen, since we are having resistive load, so from pi to next moment pi plus alpha, the output voltage will be 0, and when we will fire again T3, T4 at pi plus alpha, then what will happen, then this will be the output voltage up till the moment 2 pi, and again the same scenario will continue. So here we have T1, T2 conducting, and here we have T3, T4 conducting. So T1 and T2 are conducting from alpha to pi, and from pi plus alpha to 2 pi we have T3, T4 conducting. So if you look into that output voltage waveform, the output voltage waveform is periodic with a period of pi, where we get an output pulse for alpha to pi. So how do you write the output voltage RMS value expression? The RMS value of the output voltage will be, we have the time period which is 1 by pi, and during that time period we get the output voltage from alpha to pi, and that output voltage will be Vm sin omega t square. When we will integrate this expression, this full expression, we will get the RMS value of the output voltage. Now in order to get the RMS value of this output voltage, we have to solve this complex integration, isn't it? But you don't have to worry, because when it comes to solving the integration and the RMS value of the converters, I have seen students really struggles. Okay, so here I am telling you one trick where from which you can calculate the RMS value very easily. Okay, so if you have this kind of thing, the RMS value, guys, you can calculate very easily, and this is Vm by 2 under root 2 t, higher limit minus lower limit, plus half sine 2 omega t. Now you have to write lower limit first and then higher limit, and whole to the power 1 by 2. By using this formula as a trick, you can solve this particular integral very easily. How? Let me just show you. So we have Vm here, and what is the time period here? The time period here is pi. Okay, now high limit will be pi, and low limit is alpha. So pi minus alpha we have, plus half sine 2 omega t. What is the low limit? Low limit is alpha, and high limit is pi power 1 by 2. So now from here you can get Vm by under root 2 pi minus alpha plus half, when you put the limit you will get half sine 2 alpha power 1 by 2. So guys, this will be the RMS value of the output voltage. So in 1 or 2 step, very easily you have calculated the RMS voltage from this particular expression, isn't it? You have calculated the RMS voltage very easily by using this particular trick. Now what you have to do, you have to put the values here. So what is Vm here? So guys, source voltage is 230, and what is the firing angle? It is 45. So just put the values here. What will be V naught RMS? Source voltage is 230. So maximum value will be 230 into root 2 divided by under root 2 pi, and then we have pi is 180, alpha is given to us which is 45 degree. Now 180 minus 45, this is in degree, so you have to convert this into radians, which is pi by 180, you have to multiply by it, plus half sine 2 alpha, alpha is 45 degree whole to the power 1 by 2. So after putting the values, when you will solve this expression, you will get the output voltage to be 218.04 volt. Now after calculating the RMS value, we can very easily calculate the output RMS current by simply dividing the output RMS voltage by resistance. Okay, so what will happen? This is 218.04 and the resistance value that we have is, I think this is 10 ohm. So what will be the current, guys? The current will be 28.80 amperes. So that will be the output RMS current that we will have. Okay, so you can see here we have the resistive load, isn't it? Here we have the resistive load. So for that resistive load, one pair of switch will conduct from alpha to pi, but as the negative cycle will appear, this switch will be reverse biased. Again, when we will trigger the next pair of switch at pi plus alpha, again we will get a voltage pulse from pi plus alpha to 2 pi. So the time period will be pi and the voltage pulse is existing from alpha to pi in that duration. So this is how we can calculate the RMS value. Now the problem is to solve this particular integral because this has so many steps, and if you have mistaken anywhere, you are not going to get the correct answer. So by using this formula as trick, you can calculate the RMS value of any expression very easily, isn't it? See how easily we have calculated the answer here. Okay, yeah. So let me move to the next problem. So this is the next problem that we have, guys. See this problem. Here we have a 3-phase fully controlled bridge converter that fed from 440 volt 50 Hz AC source, and it is operating at a firing angle of 30 degree. So we have a 3-phase fully controlled bridge converter operating at a firing angle of 30 degree. The load current is assumed to be constant at 10 amperes. So the load current is constant at 10 ampere. I naught is what? I naught is given 10 ampere and it is constant due to high load inductance. Now we have to calculate what will be the input power factor. Okay, we have to calculate the input power factor. What will be the input power factor? Although we have a very easy formula for calculating the input power factor here. Okay, but how you can approach for that formula, that's also important. So guys, in a 3-phase full wave converter, in a 3-phase full wave rectifier, of course the controlled one, if you would have remembered the source current waveform is something like this. The source current waveform is something like this. From 60 to 180 we get a pulse, and then from 240 to 360 we get a pulse. Okay, the same will continue again. This is I naught and this is the source current waveform that we have. Okay, this is the source current waveform that we have. Now what will be the Fourier series expression for this source current? The Fourier series expression for this source current will be summation n equals to 135 to infinite 4 I naught upon n pi cos n pi by 6 sin n omega t plus phi n, where what is phi n? Phi n is minus of n alpha. Okay, this is the Fourier series expression for this particular waveform. Okay, now guys, how can we very easily write this particular Fourier series expression? For explaining that, I have taken another session a couple of days before. So I will post the link of that particular session in the comment box, So you can go to that video and you can see how very easily you can write the Fourier series expression for all kind of converters. Okay, so just go and visit that particular video and you will get a feel that how you can write the Fourier series expression for any of the waveform you are getting in the power electronics, so that you don't have to remember these formulas, and very easily by looking into the waveform you will be able to write the Fourier series expression for different converter. Because it will take a lot of time, so I am not going to discuss here, but I will paste the link of that video in the comment box so that you can go to that video and you can see how we can do the same things later on. Okay, now this is the source current expression that we have. Now from this source current expression, guys, what will be the fundamental source current? Or if I directly calculate, now from here tell me what will be the total RMS source current. So the total RMS source current, by looking into this particular waveform, if you calculate the RMS value of this particular waveform, you will get it under root 2 by 3 times I naught. So this will be the total, RMS current. Now what will be the current distortion factor? This is equals to IS1, fundamental RMS component, divided by the total RMS component. So fundamental component is what? Fundamental component is 4I naught upon root 2 pi cos pi by 6 divided by root 2 by 3 I naught. After this you will get CDF to be equals to 3 by pi from here. Now once you have CDF, now guys, once you have CDF, so CDF in case of 3-phase full wave converter is what? This is 3 by pi. Okay, now the power factor in case of power factor you will calculate by multiplying CDF with distortion factor. So CDF you have calculated, this is 3 by pi, and distortion factor in case of full converter is cos alpha, and in case of semi converter this is cos alpha by 2. So what will be the expression for power factor? This expression is 3 by pi cos alpha. So the expression will be 3 by pi cos alpha. Okay, you can directly remember this particular formula, but I have told you how you can approach towards this particular formula. You may get a problem in which some ratios of the component of sinusoid may be asked. Suppose if they would have asked you what is the ratio of the fifth component with respect to the first component, okay, what is the ratio of seventh component with respect to the first component. So for that you should know what is the Fourier series expression for 3-phase full wave rectifier. So for that practice I have told you how you can do, how you can approach towards that kind of problem. Okay, so similarly we have derived the power factor formula for 3-phase converter. So ultimately what it will be, 3.3 upon 3.14 cos, what is alpha here? Alpha is 30 degree. So guys, finally when you will solve it, you will get an answer 0.82. Okay, so that will be the power factor. So 0.82 is the power factor. Okay, so although we have a direct formula, but how we can approach for that formula you can see here. Okay, regarding power factor we have two popular formula. One we have here in case of 3-phase full wave converter, which is 3 by pi cos alpha, and the second when we have in case of single phase full wave control rectifier. So for single phase full wave control rectifier, let me write a note here. For single phase full wave controlled rectifier, this is 2 root 2 by pi cos alpha. Okay, so just remember these facts, guys. We have two popular formulas regarding calculation of power factor of rectifiers. One we have in case of 3-phase rectifier, another we have in case of single phase full wave converters. Okay, 3 by pi cos alpha in case of 3-phase full wave converter, and 2 root 2 by pi cos alpha in case of full wave single phase full wave converter. Okay, so just do remember these formula, because I am very sure that you can get a problem from this particular topic, from this particular formula in this upcoming GATE exam, because so many times the GATE authority has asked question from this particular topic. Okay, yeah. Now moving to this particular problem, the effect of source inductance. Okay, so this is a kind of topic where every student struggles, but you don't really have to, because I am going to reveal what you actually have to remember in order to solve these questions in GATE exam. Okay, so first of all, let me just study this question. Let me just read this particular question. In single phase fully controlled bridge rectifier, the firing angle and overlap angles are 27 and 8 degree. So guys, we have the firing angle which is 27 degree, and we have the overlap angle which is 8 degree. If it is feeding a constant output DC current, it is feeding a constant output DC current, guys. So average and RMS values are equal. Okay, 20 ampere. Then the power factor at input AC mains of 230 volt 50 hertz will be, we have to calculate the power factor. Okay, we have to calculate the power factor. So power factor, how do you calculate the power factor here? If the input power is equals to the output power delivered, then what will happen? Vs Is cos phi, this is equals to V naught I naught. Okay, these are the RMS value and these are the average values that we have. So cos phi will be V naught I naught upon Vs into Is. Now since I naught remains constant at 20 degree, so I naught and Is you may cancel, because average and RMS values will be same. So cos phi will be V naught upon Vs. So guys, we have to calculate V naught, because Vs is given to us. So once we will know what is V naught here, we can calculate the power factor very easily. So it is a single phase fully controlled converter. Okay, now how do we calculate? The power output voltage? So guys, do remember, if it is a single pulse converter, so for single pulse converter, and after that, what for a single pulse converter, if we talk about what is the average output voltage for single phase converter without LS, without source inductance, the average output voltage is how much? The average output voltage is Vm by 2 pi 1 plus cos alpha. Okay, and if you are considering the effect of LS, then what will happen? With LS, there is a reduction in this output voltage, and that reduction is given by omega LS I naught upon 2 pi or F LS I naught. Okay, this is the reduction factor. So what will be the new voltage? What will be the new voltage? You have to reduce this much amount from this much amount, and you will get the net output voltage. Okay, so the net output voltage or the new output voltage V naught new will be the old output voltage V naught average minus the reduction factor. Okay, so this is how you can remember these things. And one more thing that you have to remember is the I naught expression in case of one pulse converter. So I naught expression in case of one pulse converter will be Vm by omega Ls cos alpha minus cos alpha plus mu. Okay, so these are the things in case of a single pulse converter. When it is a two pulse converter, so these are the things in case of single pulse converter. When it is a two pulse converter, not single phase converter, it is single pulse converter. So in case of single pulse converter, we have these things. In case of two pulse converter, without LS, we have output voltage which is 2 Vm by pi cos alpha. Okay, and the reduction factor will be omega ls 2 omega ls I naught over pi, or we can write 4f ls I naught. So the new voltage V naught dash, that will be V naught average minus del V. Okay guys, so this is how you can remember these things. Now after that the current expression for I naught for 2 pulse converter, that will be Vm by 2 omega ls cos alpha minus cos alpha plus mu. Okay, so this is how you can remember these things. So only 2 or 3 things you have to remember, and let me just clarify those. Only 2 or 3 things you have to remember, guys. What are those things? For single pulse converter, what is the average output voltage? It is Vm by pi 1 plus cos alpha. What is the net reduction? The net reduction here is omega ls I naught upon 2 pi. Okay, omega ls I naught upon 2 pi, or this is equals to f ls I naught. And the current expression here is Vm upon omega ls cos alpha minus cos alpha plus mu. If it is a 2 pulse converter, if suppose this is a 2 pulse converter, the output voltage expression will be before ls, without ls. Okay, this is what? This is without ls. Now after ls, what will be the output voltage? The new output voltage will be the V naught volt minus this reduction factor. So just put the values and you can calculate these things very easily. So without ls, we have the output voltage average value 2 Vm by pi cos alpha. Okay, this is without ls, and this we have calculated with ls. So without ls, this was the expression. When ls is taken into account, the reduction in the output voltage, this will be 2 omega ls I naught over pi, or we can say 4f ls I naught, and the current expression will be Vm by 2 omega ls cos alpha minus cos alpha plus mu, and the new voltage will be V naught dash will be V naught old minus del V. Okay, so this is how you can remember these things, guys. Only these two expressions are very, very important. If you can remember this expression without ls, you know what is the formula. How much is going to be the reduction factor? You have to remember this. In single pulse, is it f ls I naught? In 2 pulse, if it is 4f ls I naught. And the current expression that we have, Vm by omega ls cos alpha minus cos alpha plus mu, and Vm by 2 omega ls cos alpha minus cos alpha plus mu. And the new voltage, if you have to calculate, you can calculate by subtracting the reduction factor from the old voltage, because when you are taking the effect of source inductance into account, there is net reduction in the output voltage. Okay, so this is how you can remember these things, guys. Now coming back to the our question. Now tell me, if we apply the formula, this is a 2 pulse converter, so we can apply the formula Vm by 2 omega ls cos alpha minus cos alpha plus mu here. So from this particular expression, the only thing that is unknown to us is ls, because I naught is given to us, and how much is I naught? I naught is 20 ampere. What will be the value of Vm here? Vm will be 2 under root 2 into 230 divided by 2 into omega will be 2 pi f. Omega is 2 pi f, or it is 314 radian per second. So you may put it directly here into ls. Cos of alpha is 27 minus cos of alpha plus mu is 35 degree. Okay, so you can see only unknown thing is ls here. So from this you can calculate ls, which will come out to be 2 millihenry, guys. Okay, so the ls will be 2 millihenry. Now we have to calculate the final target of calculation is the V naught. Okay, we have to calculate V naught here. So how we can calculate V naught, guys? So V naught will be what? V naught new will be V naught old minus del V. V naught old is 2 Vm by pi cos alpha minus the reduction factor. In case of 2 pulse converter, it is how much? It is omega ls I naught, 2 omega ls I naught upon pi, or 4fs naught, isn't it? So just put the values because we know everything here. V naught dash is, so 2 into root 2 into 230 divided by 3.14, cos of alpha is 27 minus 2 into omega is 314. ls we have calculated 2 into 10 to the power minus 3. I naught is 20 divided by 3.14. So what will be the new average output voltage? It will be 176.57 volt, isn't it? So are you guys looking into this? This is how we can remember these things very easily. Okay, when it comes to effect of source inductance, I have seen so many students struggling because guys, you are just getting into the wrong things. Okay, you can very easily remember these facts, these things, and you can solve whatever is being asked. Okay, so we have calculated V naught here, 176.57. so now what will be the power factor? Power factor, as you know, the power factor we have calculated is V naught upon Vs. So V naught is 176.57 and Vs is given 230. Okay, so what will be the power factor, guys? It will be 0.76. So this is how you can solve this problem very easy, and you can expect this particular problem into the upcoming GATE exam. I'm very sure about this, that you can expect this kind of problem in the upcoming GATE exam. I hope you have got it. Okay, now moving towards the next problem. So see what do we have here. A three-phase full bridge converter is connected to an AC supply, to a supply voltage of 230 volt per phase. Mind this word. We have 230 volt per phase. Do not ignore this fact. Okay, if you will ignore this fact, you will not able to get the correct answer. Okay, 230 volt per phase at a frequency of 50 hertz. The source inductance is 2 millihenry and the load current on DC side is constant at 18 ampere. So what has been given to us? Vs is how much? 230 per phase, guys. Okay, so in three-phase converter we require the value of VML. So what will be VML? In order to calculate the line voltage, we have to multiply this by root 3, and in order to get the maximum value we have to multiply it by root 2. Are you getting this fact? If per phase is not written here, we will only multiply this voltage by root 2. Since per phase is written and we have to determine the line voltage, so root 3 will be multiplied as well. So this will be how much? If you will calculate this, you will get 563.38 of volt of VML value. Okay, so VML will be having a value 563.38 volt. Now again, what is given to us? I naught is given, which is 18 ampere. So we have the value of I naught, which is 18 ampere. Source inductance is also given and it is having a value 2 millihenry or 2 into 10 to the power minus 3 henry. In the previous case we have calculated ls, but in this case ls is also given to us. If the load consists of a DC source of internal EMF of 380 volts, so guys, internal EMF of 380 volt is also given. with internal resistance, the R value is 0.5 ohms. Then the overlap angle will be what? We have to calculate the value of mu, and you can observe the value of firing angle is also not given to us. Okay, so we don't know what is the value of firing angle as well. Okay, so guys, first of all we can calculate the average value at the load end by applying the load side KVL, which is V naught average is E plus I naught R, and we have the required data. What is the value of E that we have? The E value is 380 plus I naught is given 18 and the resistance is having a value 0.5. So this will come out to be 389 volt. So V naught average will be 389 volts. So we have calculated V naught average. Okay. Now we have to calculate mu. So for mu, see what I have told you, without LS, what is the formula of V naught average for 3-phase converter? It is 3 VML upon pi cos alpha. Okay. What is the reduction factor? The reduction factor in case of single pulse is 2 omega ls I naught upon pi. In case of two pulse converter is, in case of single pulse converter it is omega ls I naught upon pi. In case of two pulse converter it is 2 omega ls I naught upon pi. In case of 6 pulse converter or 3-phase full wave converter, it is 3 omega ls I naught upon pi. Okay, this will be 3 omega ls I naught upon pi, where ls is the source inductance, or it is 6f ls I naught. Okay, now what will be the new voltage? New voltage will be the old voltage minus the reduction factor, or you can say here this will be 3 VML upon pi cos alpha minus 6f ls I naught. Okay, or we can write 3 omega ls I naught upon pi, whatever you want. Okay, so this will be the new voltage. Okay, now guys, if you see this particular voltage we have already calculated. Okay, we have calculated this particular voltage and the voltage is 389. So just put the values here. This is 389 here into 3 VML we have already calculated. This is 563.38. 563.38 divided by 3.14 cos of alpha minus 3 into omega. Since the frequency is 50 Hertz, so omega will be having a value 314 into ls is 2 millihenry into I naught is 18 divided by 3.14. So the only unknown value here is the value of alpha. So you can calculate the value of alpha from here, and the alpha value will be 42.26 degrees. So this will be the alpha value, guys, which you will get by solving this. So are you able to recollect the fact that by what data is required in order to solve a question related to LS? Okay, you don't have to worry about these kind of questions. You should know what is the voltage without LS, then you should know the reduction in voltage. Okay, and it is very easy to remember. Omega ls I naught upon pi, 2 omega ls I naught upon pi, 3 omega ls I naught upon pi, isn't it? See, we have written everything here. Omega ls I naught upon 2 pi, 2 omega ls I naught upon pi, and then when it comes to 3-phase converter, it is 3 omega ls I naught upon pi. Or you can say for single pulse converter, it is f ls I naught. For 2 pulse converter, it is 4 f ls I naught. For 3-phase full wave converter, it is 6 f ls I naught. Okay, so this is how you can remember what is going to be the reduction factor in voltage. The reduction factor in voltage. Then The new voltage will be what? Old voltage minus reduction factor. And see, by applying this simple formula, we have calculated the value of alpha. Now, the expression for I naught. If it is single pulse converter, we have Vm by omega Ls cos alpha minus cos alpha plus mu. This is for single pulse converter. If this is 2 pulse converter, 2 will be there. If it is 3 pulse converter, this 2 will be there and this Vm will become Vml. So guys, are you able to see how easily you can remember these formulas, isn't it? No rocket science, very easy to remember, okay? This is how you have to approach for a problem related to the overlap angle or the effect of source inductance. Now see, do we have all the data? I naught value we have, it is 18. VML we have already calculated, this is 563.38 divided by 2 into omega is 314, Ls is 2 millihenry. Then cos of alpha, we have calculated alpha which is 42.26 minus cos of alpha is 42.26 plus mu. So the only unknown quantity here is mu, guys. So on solving this particular equation, you will get the value of mu, that is the overlap angle, and this will come out to be 1.68 degrees, isn't it? So tell me guys, are you guys really feeling excited? Are you guys enjoying this problem as well? This is how very easily we are solving these tough problems. Are you getting this fact? How easily we have solved these questions related to the effect of source inductance and effect of source inductance and the different things we have calculated here, okay? So just watch this video again and again and see how we have solved these two problems, how we have approached for these two problems, guys, and you will get the feel of this topic. And I'm very sure if you get a question from this topic in the upcoming GATE exam, this will be done by you, okay? Yeah. Now, moving towards the next problem. So in this particular problem, let me just read the question first. Here we have a single phase full controlled bridge converter operates in continuous conduction mode from 320 volt 50 Hz single phase supply with a firing angle of 45 degrees. So what has been given, just note it down. We have the value of firing angle which is 45 degree, okay? The load resistance is 10 ohm. So guys, the load resistance is also given and it is 10 ohm. And a large inductance. So the load is having a large inductance as well. The ratio of fifth harmonic component to the fundamental component of source current. We have to find the ratio of I fifth to I1. What will be that? Okay. For that, we should know what is the Fourier series expression of this particular converter. So this is a single phase full wave converter, isn't it? This is single phase full wave converter. So for a single phase full wave converter, what do we have? For a single phase full wave converter, for a single phase full bridge or full wave converter rectifier, how is the source current waveform? So guys, its source current waveform is like this. The source current waveform expression is like this. If this is alpha and if this is pi, now this is pi plus alpha, now this is 2 pi and again this is 2 pi plus alpha. Okay, so how is the source current? From alpha to pi plus alpha we have T1, T2 conducting. From alpha to pi plus alpha in single phase full wave converter we have T1, T2 conducting, and from pi plus alpha to 2 pi plus alpha we have T3, T4 conducting. This is just because we have RL load here. Okay, if this is same for RL and RLE load. If this was an R load, we have already done the one problem for that. Okay, if this would have been an R load, we have already done one problem for that. So for Rn and RLE load, this will be the case. Okay, so how is the current waveform? So when T1, T2 is conducting, the source current is exactly equals to I naught, and when T3, T4 are conducting, the source current is equals to minus of I naught. So this is the source current waveform. Okay, see how very easily we have drawn this. No need to just go into so many concepts, so many things, guys. This is very easily drawn. Okay, if this would have been an R load, this current will be from alpha to pi, and from pi plus alpha to 2 pi. For RL and RE load, this will be from alpha to pi plus alpha, and from pi plus alpha to 2 pi plus alpha. Now looking into this particular waveform, what will be the Fourier series expression? The Fourier series expression will be n equals to 135 to infinite. This is a perfect square wave but shifted by some angle. So for a perfect square wave, we have 4 I naught upon n pi sine n omega t minus sine n omega t minus phi n. How is it? It is shifted. We have to shift it towards that point, so it will be phi n. Okay, yeah, we have to shift it towards left, then it will become a perfect square wave. So for a perfect square wave, this is the expression, since it is a perfect square wave. Now guys, in order to calculate the ratio of fifth to the fundamental harmonic, so in order to calculate the fifth harmonic, what will happen? The n value will be 5 here, and for fundamental the n value will be 1 here. Okay, so what will be the answer? 1 by 5. 1 by 5 is 0.2, or we can say 20%. So this is this we have solved very easily, isn't it? So see, this is very easy to remember, isn't it? How to write the Fourier series expression for different kind of converter, different types of waveform pattern. I have already taken one session. I will post the link of that session in the comment box, so you can visit that video and you guys can see how we can write the Fourier series expression, how we can very easily remember the Fourier series expression for different converter and for different waveforms. Okay, yeah. So see, we have solved this problem very easily. If you could remember the Fourier series expression, you need not to draw the waveform. If you can't remember the Fourier series expression, you have to know what is the waveform pattern. So guys, if you have the circuit, if you are studying power electronics, you can very easily draw the source current waveform here, isn't it? Yes. Moving towards the next problem, which is a very good problem, and you can expect that kind of problem in the exam as well. So just see this particular problem. A single phase half controlled converter is connected to RL load, okay, as shown in figure. This is a half controlled converter. We have 2 thyristors and 2 diodes. If the load carries a constant DC current of 20 ampere, so guys, I naught is how much? I naught is 20 ampere. The average current through diode, we have to calculate what will be the average current through this diode. Okay, what will be the average current through this diode? This is what we have to calculate. Let me give you some time for this, because I suppose you can solve this problem. So let me give you 1 minute and try to solve it. Okay, So guys, since this is a semi converter, okay, half controlled converter. So if I draw the input sine wave that we have, so let's suppose this is the input sine wave that we have. Let me mark the different angles here as well. Let this be the alpha and this is pi. Similarly, here we have pi plus alpha. This is 2 pi and this is 2 pi plus alpha. Okay. Now, if I just plot the output voltage here, now what will happen to the output voltage? See, during the positive cycle, T1 and D2 both are forward bias, but the conduction will not happen until and unless we will trigger T1. So let add the angle pi alpha, let add the angle alpha. If we trigger T1, then output voltage will exactly follow the input voltage. And what type of load we have? We have RL load here. Okay, so we have RL load here. So up till the angle pi, what will happen? Up till the angle pi, from alpha to pi, what will happen? From alpha to pi, we are having T1, D2 both conducting. Okay. Now, during that moment, the load inductance, here we have R and L. So during that moment, L has stored energy, so its polarity will be like that in beginning. Now L has to release its energy when the negative cycle is coming, so L will reverse its polarity. So that will be the inductance polarity at the end. So for that inductor polarity, guys, what will happen? D1 and D2 will be conducting from alpha to pi plus alpha. D1 and D2 will be conducting from alpha to pi plus alpha. So here we have D1, D2 conducting. Now again at pi plus alpha, the negative cycle is going on, and let's suppose inductor has released all its energy. So during the negative cycle, T2 and D1 can be triggered. So we will trigger them and the output voltage will again follow the input voltage up till the moment 2 pi. So from pi plus alpha to 2 pi, guys, which switches are conducting? We have T2 and D1 which are conducting. From 2 pi to 2 pi plus alpha, again the freewheeling will occur, and again we have from 2 pi to 2 pi plus alpha, again we have D1 and D2 conducting. So from here we can predict, here also we have D1, D2 conducting. Okay. Now since the load current is constant, guys, okay, we are given that the load current is constant. This is the I naught that we have. Now can you tell me, by looking into these waveform, what is the duration of conduction for D2? D2 starts conducting from 0. Okay, so I am just highlighting this with a new color. Let me take green here. So for D2, green represents the D2 waveform. So for D2, if you see, D2 starts conducting at omega t equals to 0 and it keeps on conducting it is not choosing the color. So we will get the D2 current. Oh, this is not happening. Just a second, guys. If we have the load current which is constant throughout the duration, And if you see the pattern of d2 that we have here, so if you see, we are getting d2 on from omega t equals to 0 up till the moment pi plus alpha. So from here onwards to here onwards, we will having the d2 current, isn't it? So d2 will be conducting from here to here, isn't it, guys? So this is the current of ID2. This is your I naught current. So you can see it starts conducting from omega t equals to 0 up till the moment pi plus alpha, isn't it? This is the ID2 current, and from the rest of the moment it will be 0. It will be again turn on at omega t equals to pi, isn't it? At omega t equals to pi, we will again have D2 conducting. So this will be the waveform of ID2. So from here you can see, if we calculate the ID2 current, average value of it, so you can see total time period is 2 pi, guys. Out of this 2 pi time period, we are having D2 conducting specifically from omega t equals to 0 to pi plus alpha. So what will be the ID2 current? The ID2 current will be I naught. ID2 current will be I naught pi plus alpha divided by 2 pi. So this will be the average value of, this will be the average value of the ID2 current. Okay, guys. So ID2 average, once we put the values, we will get the answer. So what has been given to us? I naught is 20 ampere and we have the firing angle of 45 degree. So ID2 average will be, I naught is how much? I naught is 20. So 20 pi plus pi by 4 divided by 2 pi. So once you will solve it, you will get the average diode current, and this will be 12.5 ampere. So this is how you can calculate any of the current across any of the switches, isn't it? Isn't it, guys? So we have to see from where to where the D1 or D2 diode is conducting. So D2 is conducting from omega t equals to 0. This is the common waveform for I naught and ID2. So D2 is conducting from where? D2 is conducting from omega t equals to 0 up till the moment pi plus alpha. From pi plus alpha to 2 pi it is 0, and at the moment 2 pi it again starts conducting. Okay. So the time period is 2 pi for D2 and it is existing for omega t equals to 0 up till the moment pi plus alpha. So this is how we can calculate the average value of the diode current. Okay. So this is all from the topic inverter, guys. All from the topic. This is all from the topic rectifier. The next topic that from where we are going to solve some very beautiful question is inverter. Okay. So for that I am taking a small break. We will be back after 5 minutes. So welcome back again guys after the break. So now the last topic left is inverter. Okay, so when it comes to inverter, you can expect 2 to 3 marks of question from this particular topic. And what are the important topics from where regularly the questions have been asked in the GATE exam are single phase VSI and CSI, 3-phase inverters and voltage control of inverters. Okay, so let's see one by one all the questions from this topic. So let me read the first question from here. A single phase full bridge inverter we have, voltage source inverter operating in square mode, supplies a highly inductive load. Okay, highly inductive load. The inverter time period is T. Then the duration of conduction of freewheeling diode and percentage of 7th harmonic with respect to the first R. Okay, so we have to tell for how much duration the diodes will be conducting and what will be the percentage of 7th harmonic with respect to the first one. Okay, so guys, you know that in case of single phase full bridge inverter, let me just draw the single phase full bridge inverter first. So this is my full bridge inverter that I have. It is feeding a highly inductive load. Okay, so if this is T1, this is T2, this is T3 and this is T4. If this is D1, this is D2, this is D3 and this is D4. So it is feeding a highly inductive load guys. Here we will get V0 and I0. This is Vs that we have. Now once again read the question. It is the inverter time period is T and the duration of conduction for freewheeling diode we have to calculate, and it is operating in the square wave mode. Okay, so what will be the output voltage here? Output voltage waveform if I draw, how will be the output voltage waveform here? So if I just draw the output voltage waveform here, this would be like this. See, the output voltage is, it is operating in square wave mode, so output voltage will be like this. You all know about this very well. This is T by 2 and this is T. So during the moment T by 2, T1 and T2 are conducting. So during this moment guys, we have T1, T2 conducting, and during this moment we have T3, T4 conducting, if this would have been a perfect resistive load, but it is not so here. Okay, so what will happen if this would have been a perfect resistive load? This would have been the case, but it is not so here. So what we will do here guys, what we will do here, if you see this particular waveform, if you see this particular waveform here that we are getting here, since the load is having inductance, isn't it? Since the load is having inductance, so the output current waveform will be a triangular one. The output current waveform will be a triangular one here. Yes or no? So guys, up till this moment, what will happen? Up till this moment, we have D1, D2 conducting. Here we have T1, T2 conducting. Again, here we have D3, D4 conducting, and here we have from this moment, and here again we have T3, T4 conducting, isn't it? So this is the angle phi. Now if I calculate this angle phi, the angle by which the output current is lagging, the output voltage. Okay, so this angle will be calculated by tan inverse XL by R. Since it is a purely resistive load, so XL we have some value, but the resistance value is 0 here. So we will get tan inverse infinite, or the value of phi will be 90 here. Okay guys, so the value of phi will be 90 here. So this will be a midpoint here. So if this is t by 2 duration, this is surely going to be the duration t by 4, isn't it? So d1 d2 will conduct for how much duration? d1 d2 will conduct for t by 4 duration. Okay guys, if the load is purely resistive, the diodes will not conduct. T1, T2 or T3, T4, they will conduct for T by 2 duration. If the load is purely inductive load, then diodes will conduct for T by 4 duration, and the thyristors will also conduct for T by 4 duration. If this would have been an RLC load, then definitely this particular duration will not be T by 4, T by 4 even less than T by 4, and that is determined by phi, which is tan inverse XL minus XC upon 4, if this would have been an RLC load. Okay, so this is how we will do this particular thing here. Now as you can see, the output voltage waveform that we have plotted is a perfect sine wave, perfect square wave. So in case of a perfect square wave, if I write the Fourier series expression for output, what will be the Fourier series expression for output? N equals to 135 to infinite. Since it is a pure square, perfect square wave, the expression will be sine n omega naught t. Again, I need not to tell, just visit the link that I am going to paste right after this session into the comment box, where you will get how to write the Fourier series expression for different converters. Okay, so what we have to calculate? We have to calculate V07 upon V0 first. So guys, what will be V07 here? V07 here will be 4Vs upon 7 pi, and this will be 4Vs upon pi. So you will get 1 by 7 or 0.143, or you can say 14.3%. So the ratio of 7th to the first harmonic will be 14.3% here, isn't it? This ratio will be this much here. So option B and C are the correct options. I hope you are getting this particular problem. Okay, this might be a key problem in your upcoming GATE exam. Now see this particular problem. Again, the same principle we have to utilize here as well. Read the problem with me. In a single phase full bridge inverter, as shown in figure below, is operating at a fundamental frequency of 50 Hz. The RMS value of fundamental component of load current in ampere will be. The RMS value of fundamental load current we have to determine. RMS value of fundamental load current. What will be that? We have to determine this. The value of inductance L is given 0.1 Henry, and the frequency is how much? 50. So guys, first of all calculate XL. What is XL? XL is omega L or 2 pi FL. So how much will be the XL? 2 into 3.14 into 50 into 0.1. So this will be 31.4 ohms. Okay, so this will be 31.4 ohm. That will be the value of XL. Now we have to calculate the fundamental value component RMS value of current. So guys, what is the output voltage expression for single phase full wave inverter? We have already written in the previous problem. So we have 4 Vs upon n pi sine n omega t. Now what will be the current? So in order to calculate the current, what you will do, this will be 135 to infinite 4 Vs upon n pi. You will divide it by Zn angle phi n, the impedance. Okay. Now what do we have in our case? In our case, now let me just write this once again. This will be 135 to infinite 4 Vs upon n pi Zn sine n omega t minus phi n we will have. omega t minus phi n will be there. Now we have to calculate the fundamental component and its RMS value. So what will happen? This will become 4 Vs upon n will be 1. For RMS we have to divide it by root 2 pi, and Zn we have 31, Z1 we have 31.8. Okay. So just put the values here. Vs is how much? Vs is given to us 1100. So this is 1100 root 2 into 3.14 into 31.8. So can you calculate how much RMS component of current will be, guys? So the RMS component of current will be 31.56 amperes here. Okay. So if you can just remember this particular formula, of the Fourier series expression of single phase full bridge inverter, you can solve n number of problems very easily. Okay. Yes, you can solve n number of problems very easily. So in the last problem we were about to calculate the ratios of two harmonic voltages. Here we have to calculate the fundamental component of current. For that you should know the expression of output voltage of Fourier series expression of output voltage of inverter. If you know that, you can calculate this very easily. Okay. Now after that, if you are able to solve this, I am sure you can solve this problem very easily. So just read me out. In a single phase full bridge inverter as shown in figure below is operating at a fundamental frequency of 50 Hz. Okay. The peak value of load current is ampere. Guys, we have to calculate the peak value of load current. Okay. We have to calculate the peak value of load current, and your time starts now. It's very easy problem. So I am giving you 1 minute for this. Five seconds. So guys, if you have remember, for a pure inductive load, I have drawn the current waveform in the previous problem, and the current waveform is having this particular shape, and it is varying in a triangular manner where it has its value minus IP and plus IP. Okay. So for this particular moment, if you see, here we have T1, T2 conducting, and here we have T3, T4 conducting. So this duration is exactly T by 2, isn't it? This duration is exactly T by 2. And here we have T. Okay. So you can see when T1 and T2 are conducting, the inductor current is varying from minus IP to plus IP. When T3, T4 will be conducting, or here we have S1, S2 and S3, S4. So when S1, S2 will be conducting, in this particular moment we have S1, S2 conducting, and in this particular moment we have S3, S4 conducting. Okay. So when S1, S2 are conducting, for that T by 2 period, the current increases from minus IP to plus IP, isn't it? Isn't it? And guys, if this is the source voltage, and here we have the load voltage, and that is the inductor voltage as well. So what do we have here? So we have here, when any of the switches are conducting, we have VL exactly equals to VS. You know that VL is L d I naught by dt. This is equals to Vs. Now what is di naught? The change in the inductor current pattern. So inductor current is changing from minus Ip to plus Ip. So what will be the net change, guys? The net change will be Ip minus of Ip. And what is the time period in which this change is happening? It is T by 2. So what will happen? L. Oh, I have written that here. So L, I have to write this here, okay? So what we have to do, the change in current is Ip minus Ip divided by T by 2, and here we have Vs. So guys, this will be 2 Ip divided by T by 2 equals to Vs, or we have Ip equals to what? Vs upon 4 FL, okay? So this is the expression for Ip for a single phase full bridge inverter, Vs upon 4 FL, okay, for single phase full bridge inverter. For single phase full bridge inverter, we have this particular expression, okay. And if suppose this would have been a half wave converter, instead of Vs we have Vs by 2 here. So Ip expression would have been Vs upon 8 FL if this would have been single phase half bridge inverter. So for single phase half bridge inverter, we have this particular expression. But since we have single phase full bridge inverter, okay, so we will use this particular expression. And what will be the Ip value? Ip value is Vs, which is 100 upon 4, F, which is 50, into the L value, which is 0.1, okay. So just put the values and calculate the answer. So what is going to be the Ip value, guys? What is going to be the Ip value here? The Ip value will be, what will be the Ip value here? Can you calculate this for me? Can you just calculate this for me? This will be 55 amperes, okay. So this will be the Ip value. Now here we have single phase full bridge inverter. Be ready for a problem where instead of single phase full bridge inverter, you will get single phase half bridge inverter, and the same calculation you have to do, but you have to use this formula Vs upon 8 FL, and you can solve this problem very easily, isn't it? Yes. Now let me move to another question which is very good. Now in this question we have a single bridge inverter that delivers power to a series connected RLC load with R equals to 3 ohm, omega L equals to 12 ohm. Now the inverter switching frequency is 10 to the power 4 Hz. The value of capacitance required in the load to obtain load commutation for the SCR in microfarad will be what? That we have to calculate. Circuit turn off time is also given to us, which is 15 microseconds. So guys, here we have single phase full bridge inverter which is feeding to RLC load, okay. It is feeding to RLC load. So by the angle by which the output current will lead or lag, the voltage is given by what? And see, in this particular problem, in order to have load commutation possible, so if you want to have load commutation, your RLC load must be under damped. That is, the value of capacitance must be greater than the value of inductance, okay. So for the load commutation to be possible, the load must be under damped, okay. The load must be under damped, and if the load is under damped, guys, the angle by which the current is leading, the load must be under damped means Xc must be greater than XL, or the current must be leading, okay. So by the angle by which the current will lead the voltage is given by this particular expression, okay. Now theta, how do we calculate theta here? So guys, theta is that omega Tc instant on that if you see in this curve, which we have drawn here, this is the omega t, and phi is what? Phi is that duration by which the current is leading or lagging the voltage, guys. So what do we have here? This omega t will be equals to theta, or we can calculate theta by using omega tc. So what is the value of theta, guys? Omega is what? 2 into pi into f. So 2 into pi into f is what? 10 to the power 4, and tc is the circuit turn of time which is given to us, which is 15 microseconds. Okay, so when you will solve it, you will get 0.94 from here, but it will be in radian. So when you will convert it into degree, you will get 54 degree here. Okay, so when you will put here 54, tan inverse xc we have to calculate, xl, that is omega l, is given to us 12 and r is 3. So the only unknown thing here is xc. So xc will be, if you calculate from this expression, the xc will be 16.11. Okay, now once you have calculated xc, xc you know is 1 upon 2 pi fc. This is equals to 16.11, and everything is given to us. Now you can calculate the value of c from here, which is coming out to be approximately 1 microfarad. So this will be the answer. So this is how you can calculate the value of c here. Okay, guys, this is also very interesting problem, one of the fundamental problem I should say, and this may be asked in the exam. Okay, I am expecting this to be a question in this particular upcoming GATE exam, guys. Okay, so this is a very important problem, and I hope this is very clear to you. Now moving towards the next problem. What has been asked in this question is, in the current source inverter CSI shown below, the load is purely resistive. We have a purely resistive load. The maximum output frequency obtainable will be, we have to calculate what will be the F max. Okay, so this is an ASCII inverter. This is an ASCII CSI inverter, guys. So in that case, we have a very popular expression to calculate the maximum frequency. This maximum frequency is 1 upon 4 RC. You don't have to do anything, just put the values and calculate the answer. What is the value of R? It is 8. What is the value of C? It is 0.2 microfarad. So from here you can calculate the value of value of F. And can you tell me what is going to be the value of L? This will be 156.2 kilohertz. So I hope this is very clear to you guys. You have to remember only this small formula, that F is equals to what? F is equals to 1 by 4 C. Okay, and you will always see these C identical values of capacitor here. Okay, if the capacitors are not identical, then we have to do something else, but you will definitely not going to see that particular case in GATE exam. Okay, only remember this particular formula of ASCII inverter to calculate the maximum frequency, and by using this formula you can calculate it very easily. Okay, so after this I have a very beautiful question, very important question as well, because this type of question has never been asked in the GATE exam. So I am expecting this to be the next GATE question, guys. What has been given to us is a 3-phase bridge inverter delivers power to a resistive load from a 400 volt DC source for a star connected load of 10 ohm per phase. The ratio of power delivered to the load when inverter is operated in 180 degree and 120 degree mode respectively. Okay, so in 3-phase, guys, how do we calculate power? For a 3-phase power, this is equals to, and for a pure resistive load, this will be equals to 3 V phase square by R. So we should know what is the value of phase voltage in case of 180 degree inverter and in case of 120 degree inverter. So guys, if it is a 180 degree inverter, okay, So if it is a 180-degree inverter, the value of line voltage is root 2 by 3 Vs, and the value of phase voltage is just divided by root 3, and you will get root 2 by 3 Vs. For 120-degree inverter, the value of line voltage is Vs by root 2, and the value of phase voltage is Vs by root 6. Okay. If you can remember these formula, nobody can stop you gaining marks for this particular question. Okay. So first of all, we have to calculate the power in case of 180-degree inverter. So in 180-degree inverter, this is 3 V phase square divided by R, or 3, what is V phase? It is root 2 by 3. The value of Vs is how much? It is 400. Yes, it is 400. So that value is 400 square divided by the value of resistance is 10 ohm. So when you will solve it, you will get 10.66 kilowatt of power. Similarly, in case of 120-degree inverter, this is 3 V phase square by R, or 3, what is the V phase voltage in case of 120-degree inverter? This is Vs by root 6. So Vs by root 6, or directly we can put the values because we have written the formulas already. So what will be the value? Vs is 400 divided by root 6 square divided by 10. So what will be the answer, guys? You will get 8 kilowatt from here. Now what we have to do? We have to calculate the ratio of power in 180-degree inverter to the ratio of power in 120-degree inverter. So this will be 10.66 divided by 8. So what will be the ratio? This ratio is going to be 1.33. So this is how you can solve this problem very easily, isn't it? Only thing that you have to do is to remember the line voltage and phase voltage formulas in 180-degree and 120-degree inverter, isn't it? If you could remember the formula, you can solve this particular problem very easily, isn't it? And guys, this is a kind of problem which may be asked in a something different manner. How to calculate the power, you should know only that thing, and you will be able to calculate these things. Okay. Yeah. So let me move to the next problem. Now see this problem. This is also a very important and very, what I have to say, very difficult one as well, isn't it? A three-phase voltage source inverter as shown in the figure is feeding a delta connected load. So we have three-phase VSI which is feeding a delta connected load. Okay. It is fed from 600 volt battery. Vs is 600 volt and 180-degree conduction of solid state devices. The reactive power consumed will be, guys, I'm very sure you are going to get this particular question in the upcoming GATE exam. We have to calculate the reactive power here. We have delta connected load. So it is a delta connected load. So in delta, the value of load is what? 50 plus 50J, isn't it? So when you will convert this load from delta to star, the per phase impedance will be what? You have to divide it by 3 only, because if we have 3 resistances connected in delta, if you are converting them into star, what will be the equivalent star resistance? It will be R by 3, isn't it? So when you will convert it into star, you will get this particular value of star impedance per phase. Okay, so we have this particular value of star impedance per phase. Now we have to calculate the reactive power. Before that, we have calculated the active power in the previous problem. So for calculation of reactive power, it will be 3 V phase square upon X only, isn't it? Reactive power, we have to calculate the reactive power. So if you are dividing by R, you are calculating active power. Dividing by X, you are calculating the reactive power, if you divide by Z, you will actually calculate the complex power. So we have to calculate here the reactive power. And which type of inverter we have? It is 180-degree inverter. So in case of sorry, in case of 180-degree inverter, what is the phase voltage? The value of phase voltage is Vs under root 2 by 3, isn't it? So just write these values here and you will calculate what is required. Root 2 by 3 into Vs is 600 square divided by the value of X is 16.66, isn't it? So when you will solve this, you will get the answer required, and it is 14.40 kVAR. This will be the reactive power required. So in the previous problem we have calculated the active power. In this problem we are calculating the reactive power. Okay. Now this problem may be changed. Instead of 180-degree inverter, you might get 120-degree inverter. Okay. So only thing that you have to do is to remember these expression, and nobody can stop you gaining marks for this kind of questions. Okay. Whether it is active power, whether it is reactive power, or whether it is a calculation of the ratios or the difference of power may be asked. The question may be modified in different manner, guys, but the way of doing this particular question will remain same, isn't it? Yeah. Now this is a very important problem, I have to say. I think you remember that in yesterday's session the last 3 problems that we have were really fantastic problem, isn't it? Similarly, I have the last 3 problems here as well, which you are really going to enjoy. Okay. Now this is a kind of problem which I really like the most, because in this problem we have a combination of choppers and the inverter. So let me read the problem first, and then you will see how beautiful this problem is, how important this problem is. A chopper is providing input to the 3-phase 120-degree voltage source inverter. It is a 120-degree VSI. As shown in figure below, the chopper is operating at a duty ratio of 0.8. So guys, duty ratio is given 0.8. Okay. Then the total power dissipated across the load will be how much we have to calculate. So if you see, in case of 120-degree inverter, so what will be the power across this? What will be the power across this 120-degree inverter? This will be 3 V phase square by R, isn't it? Now what is the V phase voltage? What is the V phase voltage of 120-degree inverter? The V phase voltage of 120-degree inverter is Vs by root 6 divided by R, isn't it? So guys, we don't know what is the value of Vs, because Vs will be here. Vs will be here, and this Vs is coming out from this boost converter. This is the boost converter that we have. Okay. So in case of boost converter, the output of this boost converter, whatever is the output of this boost converter, that will be the input to the inverter. So how do you calculate the output of the boost converter? Output of the boost converter will be 220 upon 1 minus D. So 220 upon 1 minus D is how much? D is 0.8. So guys, what is going to be the V naught here? What is going to be the V naught here? V naught here is going to be 1100. So guys, this voltage will act now as input to this, input DC to this inverter, and this will be the Vs in this case. Now put the values and get the answer. So this is 1100 divided by root 6 square divided by the resistance value is 20. Okay. So how much answer you are getting from here? You will get 30.25 kilowatt. 30.25 kilowatt. So do we have any answer? Yes, option A. Option A is the correct answer, isn't it? Now this problem may be asked in maybe in some other mode as well. Instead of boost converter, this might be a buck converter, this might be a buck boost converter, guys. So you should know the expression of output voltage of buck boost or buck boost converter, and after that, and that we have discussed in the last session that I have taken on yesterday. And if you know the output voltage expression of different converter, So the output of the particular converter is the input for the VSI, and you can solve. After that you can solve this problem very easily. Okay, let me correct this. This is 120 here. Okay, this is 120 here. In the problem you can see it is written 120, but here it was written 120. So this also may be a case. Okay, instead of 120, either they can change the converter here, or either they can change here. Instead of 120 they might ask you 180 as well. Okay, so be ready for that kind of problem as well. So isn't it a very beautiful problem, a problem that you may expect in the upcoming GATE exam? Be ready for that. Now see this problem, guys. Okay, a single phase full bridge inverter has maximum fundamental output voltage of 300 volt. It has maximum fundamental output voltage of 300 volt. The output voltage is now controlled by using single pulse width modulation with pulse width of 72 degree. So guys, pulse width 2D is 72 degree here per half cycle. The total RMS is reduced by 1/4 of its value, then the power delivered to the load resistance of 10 ohm will be. So many twists and turns are there in this particular problem. So when we have not used the pulse width modulation, before that what has been given to us? Before that we have maximum fundamental output voltage, which is 300 volt. So without pulse width modulation, without PWM, guys, you know the output voltage expression for single phase full bridge VSI, and that is what? That is 4 Vs upon n pi sine n omega t. Now what will be the fundamental maximum value? So for fundamental maximum value, this will be equals to 4 Vs, n value will be 1 upon pi. Now this is given to equal to 300, 4 into Vs upon pi. So from there you can calculate the value of Vs. For calculation of Vs, this particular data was given to us. So what will be the value of Vs, guys? Vs value will be 235.5 volt here. So we have the Vs value right now. So the Vs value is 235.5 volt right now, and the pulse width is 2D. Okay, so before we have employed the pulse width modulation, from the given data we have calculated the Vs value. Okay, now we are employing the pulse width modulation. So when we are employing the pulse width modulation, the total RMS value of voltage will be what? With PWM. So with PWM, the total fundamental voltage, total RMS value of voltage will be what? This is calculated by Vs under root 2D upon pi. Okay, this is the pulse width that we have here. So now you have everything to calculate this. Vs is 235.5. 2D is the pulse width that we have is 72 divided by 180. So from here you can get the total RMS voltage after employing the pulse width modulation, and that will be 148.94 volts. So that will be the voltage after employing the pulse width modulation. Now this is not the end of the problem. One more thing is given. If the total RMS is now reduced by 1/4 to its value, now the effective RMS value is what? The effective RMS value is what? V dash RMS, if I write it, this is what? This is the total RMS divided by 4, because 1/4 we have to take. So 148.94, this is now being divided by 4. So when you will divide it by 4, you will get 37.23 volt is of the voltage. Now when we have divided it by 1/4, then what is the power delivered to a resistance of 10 ohm? Guys, what is left now? Now we have to calculate the power. So this will be V dash RMS square divided by R. So 37.23 square divided by 10, which is the resistance. So you will get the power in that case, which is 138.65 of watts, isn't it? So this is how we can solve this problem. So many twists and turns were there in this problem, and that's the reason why I have designed this case. Okay, so before we have used the pulse width modulation, what is the maximum possible fundamental voltage that is given to us? From that data we will determine the value of Vs. When we have used the pulse width modulation, then after that, what is the total RMS value? We have determined that, and it has been given that 1/4 of value is used only, so we have divided it by 1/4. Then we have to calculate the power. Okay, so we have calculated the power as well. Now one mistake that generally you will do here, okay, what you will do by looking into the problem that it belongs to the pulse width modulation case, you will use the output voltage formula, which is this one, 4 Vs upon n pi sine nd sine n pi by 2 sine n omega t. Guys, we don't have to use this. This formula is required when pulse width modulation is used. Okay, so the maximum fundamental value that has been given to us is before PWM. Okay, if after PWM this would have been given, we would have used this particular formula. Okay, this particular formula Fourier series, but this was before PWM, so we have to use this particular Fourier series formula, which is for single phase full bridge inverter without PWM, isn't it? So just remember this fact. This problem has so many twists and turns. Okay, so be very careful, and I'm very sure you can expect this kind of problem in exam as well. Okay, do not mistake and do not take this formula. This is a reminder for you. Now moving to the next problem, and one of my favorite one. Okay, I have designed this particular question because I'm very sure, because now the times from the topic inverter, gate authorities are asking questions related to modulation index. Last time as well, in the year 2022 as well, we have a question from modulation index. And 1 year before, in the 2021, 2019, 2018, we have a question related to modulation index as well. And that's the purpose of including this problem as well, to get you better practice of this topic in this particular booster series as well. Okay, so guys, this is a very well designed problem. Just read this with me, and I will tell you how you can approach for these kinds of problem. So what has been given in this problem is a single phase voltage source inverter is feeding an RL load as shown in figure. It is controlled by SPWM technique. The reference sinusoid wave VR and triangular wave VC of 10 kHz frequency are shown below. So we have VR and VC waveform shown to us. The VR waveform, okay, the reference voltage decides the frequency of the output of the inverter, and the carrier wave decides the switching frequency of the inverter at which the inverter switches are switching. Are you getting this fact? Why do we have two waves here? The reference wave will decide the output frequency of the inverter, and the carrier wave is going to decide at what particular frequency the inverter switches will be switching. Okay, so that is the purpose of these two waveforms. Now here you can see the peak of carrier. The peak of carrier is how much, guys? If you see, the peak of carrier here is 2 volt, and what is the peak of reference? So if you see, the peak of reference is 1 volt here. So immediately you can calculate the modulation index. Okay, you can calculate the modulation index MA, which is the peak of reference to the peak of carrier. Okay, the peak of reference to the peak of carrier. the modulation index, peak of reference to the peak of carrier. Okay, so reference is 1 volt and the carrier is 2, so you can calculate it. The modulation index is 0.5. So immediately do this little one. Okay, you can calculate the modulation index by looking into the waveform as well. For the further reference, just read the problem. The reference wave is given by VR equals to 1 sin 100 pi t. R is 8 ohm and XL is 12 ohm at 50 hertz. Then RMS value of fundamental component of current will be what? What we have to calculate here is, we have to calculate the RMS value of fundamental component of current. This is what we have to calculate, and we are given with the R value and the XL value. What are those values? R value is 8 ohm and XL value is 12 ohm. This is 8 ohm and this is 12 ohm. So guys, to calculate the impedance immediately, which will be R square plus XL square, or which will be 8 square plus 12 square. So what is going to be the Z here? The Z value will be 14.42 ohm. Okay, now we have to calculate the fundamental RMS current. For that, impedance is also given. So if we are able to calculate the voltage, we can calculate the current by dividing it by impedance, isn't it? So guys, fundamental peak, this is equals to modulation index times Vs, if this is single phase full bridge inverter. Just remember these formulas and you will score 2 marks in GATE exam by just remembering this formula. Full wave inverter, okay, for single phase full wave inverter, full bridge inverter. If suppose this is half bridge inverter, you will use Vs by 2. This is for single phase half bridge inverter. Okay, this is for single phase half bridge inverter. And if this, suppose this would have been 3-phase inverter, then we would have calculated the line to line fundamental component, peak of line to line component, and that will be root 3 MA Vs by 2. This is for 3-phase inverter. So just remember these formula. These are very, very important for you. If this would have been a single phase full wave inverter, the fundamental voltage peak value will be MA into Vs, where MA is the modulation index. If this would have been single phase half bridge inverter, the fundamental peak will have a value of MA Vs by 2. And if this would have been a 3-phase inverter, the line to line fundamental peak value will be root 3 MA Vs by 2. Just remember these formula and you can solve n number of problems. Nothing will come out of this. I am very, very sure about this. All you need to do is remember this formula. So what do we have in our case? In our case, we have single phase full bridge inverter. So which formula we will use? For calculation of fundamental peak, we will use this formula, MA into Vs. Now if we calculate the RMS value, what we have to do? In order to calculate the RMS value, we have to divide it by root 2. That you can do in any of the formula. That depends whether the peak value has been asked or the RMS value has been asked. Okay, as per the requirement you will do it. So MA is given us, that is 0.5, and what is Vs guys? Vs is 500. Vs is 500 divided by root 2. So that will be the output voltage, and this is coming out to be 176.80 volt. This is 176.80 volt. Now, where we have to calculate the RMS fundamental component of current. So that will be the RMS fundamental component of voltage divided by Z. Okay. So we have all the values with us. This is 176.8 and Z value is 14.42. So the fundamental component will be 12.126. Okay, so we have calculated this. So fundamental of component of current and its RMS value is 12.126. 0.26 ampere. That is what we have calculated. I hope you are getting this, guys, and this is very, very important. Believe me, this is very, very important. Okay. Last year we have seen a question from modulation index. Before that, in the year 2022, there was a question from modulation index. Before that, in the year 2017-18, we have a question from modulation index. So this particular topic from the inverter is very, very important. Okay. Yes. So I hope this is clear to you. Now what can be changed in this problem? In place of single phase full wave inverter, maybe single phase half wave inverter is there, maybe three phase inverter is there. So you have to use the fundamental peak formula according to the requirement of the converter, and the rest of the things will be same. Okay. Yes. Now see this particular problem. A single phase full bridge inverter is operated at 60 Hertz. So frequency is given to us, and that frequency is 60 Hz. Now, with multiple pulse width modulation technique, multiple pulse width modulation technique is involved here. A triangular carrier wave of 2 volt, triangular carrier wave of 2 volt, and the frequency of carrier is 1.2 kilohertz. Okay, is compared to the reference square wave of 1 volt. Reference square wave of 1 volt. Okay. Now, what will be the frequency of reference? So, I have told you the frequency of reference is going to decide the output frequency of the inverter. The carrier frequency is going to decide the switching frequency of the inverter. So, guys, what is the operating frequency of inverter? It is 60 Hertz here. So, the reference frequency will be 60 Hertz, isn't it? This is the data that we have. The zero of triangular wave coincides with the zero of reference wave. So when this particular thing is there, zero of reference is coinciding with the zero of reference and carrier are coinciding with each other. In that case, the number of pulse fed per half cycle, the number of pulse fed per half cycle are Fc upon 2Fr minus 1. Okay, when zero of both are coinciding, when zero of both are coinciding, in that case we will use this particular formula. If suppose the peak and zero are coinciding, then we will use this formula. Okay, this is when peak and zero of reference are coinciding. Then we will use this formula. So what is the case here that we have? In our case, both the zeros are coinciding. So guys, the number of pulse fed per half cycle will be Fc upon 2Fr minus 1. So what is Fc? Fc is 1.2 kilohertz divided by 2 into Fr is 60 minus 1. So can you tell me how many number of pulses will be fed per half cycle? This is going to be 9. Okay. Now we have to calculate the pulse width of each pulse. So guys, the pulse width, or we have to say each pulse width. So guys, the each pulse width in case of multiple pulse width modulation is 2D upon n. Okay, each pulse width, and this is equals to 1 minus VR upon VC pi by n. So put the values here. What is the value of VR? It is 1. VC 1 by 2. Pi number of pulses are 9. So how much you are getting from here? Pi by 18, or I have to say 180 upon 18, that is 10 degree. So do we have any option? Yes, option A is the correct answer. So are you getting this particular problem, guys? This may also be an important case, isn't it? Isn't it? This may also be an important case, guys. Yes. So this is all about, guys, this is all about the inverter as well. So now we have completed the complete syllabus of power electronics, and yesterday and today we have almost discussed more than 60 questions, and these questions are very important as far as the GATE exam is concerned. Now watch these videos again and again, guys, and the way I have recalled the particular formula required to solve any problem, try to make your approach like that. If you are really doing so, you will not fear anymore about power electronics. It is a very scoring subject, guys. In the year 2022, in the year GATE, in the year 2022, the power electronics that has 13 marks associated with it. Power electronic, this subject has 12 to 13 marks of questions coming out of it, and those questions were really very easy questions, guys. If you have seriously practiced power electronics, if you just watch these videos of mine that I have taken yesterday and today again and again, and the way I have approached towards a particular problem, the formula required for solving a particular problem, how we can make ourselves approachable towards a particular formula without even remembering, without even bothering to remember a particular formula. Just see this video and try to recognize these facts, try to practice these problems. We have almost solved 60 plus problems here, and guys, practice these problems, and I'm very sure you are going to do very well in this subject, power electronics. Okay, just watch this video as much as you can and share these videos with your friends as well, so that everybody will be benefited. Okay, yes, so this is the end of this particular subject, power electronics, in this GATE booster series. Okay, now if you have really enjoyed yesterday and today's session, and if you really want to join us to have a permanent joy and permanent what we have to say, if you want to enjoy the excellent teaching, and if you really want to learn, practice and test yourself, join us, because we are offering something that is nobody is doing here. So let me reveal about the IMS GATE Academy features as well. So you can visit our website, which is www.imsindia.com, and you can see our features. Okay, so guys, we are offering 4 programs. The first one is the classroom program, second one is the hybrid classroom program, and third one is exclusively live offline program, and the fourth one is self-learning program. Now what all these programs are all about, let me just reveal one by one. So if you join our classroom program, we will offer you 750 hours of offline classroom session, 100% offline. So once you will join us, we will give you 20 to 30 books that consist of theory books and exercise book. Theory books we have designed in such a manner that are very crisp and the perfect material for any GATE aspirants. After that, you can see our exercise book, which have 4,000 plus practice questions. So if you really practice that amount of questions, you need not to do anything else. Okay, then we have GQB, the GATE question booklet, where you can see the old GATE questions and the multiple ways through which you can solve the GATE questions. We have a dedicated doubt solving portal that also we are offering, my plan session, our test series we will offer you, and post GATE guidance we will also offer you if you join us in offline manner. After that, we also have a hybrid classroom program, where the 2/3 content will be delivered to you in online manner and 1/3 content will be delivered to you in online manner. So 2/3 in offline and 1/3 in online, and rest all the packages remain same. You will get everything that you are getting there if you join us in offline manner. Okay, now exclusively live online program. Guys, I know that it's very difficult to manage the college studies as well as the preparation. So if you are really struggling with that problem, you don't have to worry, because the GATE is coming live at your home. Okay, so we are offering exclusively live program as well, where we are offering 750 plus hours of live online sessions as well, where this number of hours will be delivered to you in an online manner right after your college. Okay, the timing that we have planned is such a manner that these classes will run right after your college, so it's become very easy to manage both college and preparation at the same time. And the same package you will get which you were getting in hybrid and offline classes. Okay. And if you are really struggling to manage the time, you can join our self-learning program as well, where we are offering you 400 plus hours of video lecture in recorded manner. And this much of package you will also get. Apart from the test series, you will get everything here as well. So if you are really struggling to manage time, you can join us in self-learning mode, self-learning program that we are offering, where we will give you the recorded content. Okay. Now, we believe in learn, practice and test methodology. Okay. So, first of all, we will make you learn the concepts, the tricks and whatever required for the gate, and then we are giving you material from where you can practice enough to score much in the gate exam. And when you have learn and practice, then we are offering 130 plus test in our test series, so you can have a better practice before you actually appear to the gate exam. Now, these number of tests we are offering, guys, we are offering you 84 plus chapter test, 12 basic level subject test, 12 advanced level subject test, and 8 multi-subject test, and 12th AIMTS test. Okay. So guys, you have seen yesterday and tomorrow the kind of question that we people have solved are unmatchable, isn't it? So if you really want to enjoy that kind of experience, you can join our test series, you can see our test series, and I'm very sure you will get a great experience out of it. Okay. Now, if you really want to join us, you can join us. Before you actually join us in a permanent manner, you can join our zero fee program as well, where we are offering you 100 plus hours of concept videos, 12 chapter test, 6 subject tests and 6 past gate papers, and this everything is delivered to you at free of cost. So you can join us without paying anything. That is called zero fee program. So join us and check everything. If you really like us, then you can join us in a permanent manner. Okay. So this is a zero fee program that we are offering, nobody else is doing. Before actually joining us, you can check our content, our material, everything. Okay. Now, this is the appearance of doubt portal. This is the appearance of student portal, how this is going to look. In that you can see there is a doubt portal as well. So this is the appearance of doubt portal. Suppose you are solving any problem from our content, our material, or from anywhere else in the world, and if you are getting any doubt, okay, then you can post your doubt immediately on our dedicated doubt portal, and that doubt will be solved within 24 hours. So that is something that we are offering, guys. After that, while you are preparing, you have so many doubts, okay, you have so many questions in your mind, how to learn, how to practice, how to learn a particular subject, how to deal the core subject, how to deal the common subjects, how to revise the things effectively, what to do and what not to do if you are appearing in the gate exam. So if you are really wondering with these questions, in order to solve these questions, guys, we are having one-to-one mentoring session where you can interact with us personally and you can share your doubts, you can share your query with us, and we will resolve this on the spot. Okay. We also have one-to-many mentoring where many students can just have a dialogue with us. Okay. Now, we are currently going to announce new batches. So guys, our new batches are going to be conducted very soon. Live online new batch that we are going to open from 3rd of January. Okay. So live online batch is starting from 3rd of January, where we will start signals and system for EC electrical IN, and from 7th of January we are starting networks as well. So if you are EC electrical IN student, you can join us on 3rd and 7th of January, where we are starting signal and system and networks. Okay, and these are the numbers through which you can ask any of your queries and you can join us. Classroom program. If you want to enjoy classroom program, then we are offering offline classroom program. From 8th of January, we are starting digital there at Jayanagar for Bangalore students. Okay, this is for Bangalore students. We are starting our offline batch from 8th of January and we are going to start digital there. Now, GATE hybrid program. The GATE hybrid program is also starting from 3rd of January. We will start signal and system there. And from 8th of January, we are starting control system at Vijayawada Center. Okay, so Vijayawada students, note down this number. If you really want to join us, you can call us or message us. So our new batches are going to start at Vijayawada in hybrid manner from 3rd of January and 8th of January. Okay, so this is the end of today's session, guys. I hope you people have really enjoyed today's session and the yesterday's session as well. So we have almost solved 60 plus problem. Again and again, just look into these problems. Just look into the approach that we have adopted together to solve a question. And I'm very sure you are going to get any of these questions coming into the GATE exam in this particular year. So if you are well prepared for the GATE exam, these are really going to boost your score. And if you think you are not in a great touch of the subject, just solve these questions and the approach that we have discussed. After solving, I'm very sure you will feel that now your preparation has moved to the next level. So this is the end of the session today. Thank you so much for being there and listening to me and solving the questions together with me. Now I will come again live on 29th and 30th of December to discuss some fascinating questions of power system. Some very good questions of power system and some good concepts of power system will also be discussed there. So be there on 29th of December and 30th of December, where I will again come live and discuss power system gear. So thank you so much, guys. Best of luck for the upcoming GATE exam. Thank you so much.